Yeah, so
today we are pleased to have another session of our seminar, and today's speaker is Filip Strakoš from Uppsala University, ex-Charles University, who will tell us about augmentations of Chekanov-Eliashberg algebra and geography of Bilinearized Legendrian contact homology. Please, Filip.
Thank you very much for the introduction. This is a seminar about cohomology and homology in different settings. So maybe before I will start saying something serious, let me digress on some philosophy, how homology and cohomology arises and appears in topology. So what we actually do, we fix a ring which is nice enough, and we in topology want to study spaces up to some equivalence. And from the space, using some topological construction, we get the chain complex over our ring. And then from the chain complex, we get the homology. However, we also, like usually we have a lot of those spaces, and a lot of those spaces are similar in a way. So we can have or we define an equivalence of spaces, and we study them up to this equivalence. And then we want to choose our construction nice enough so that somehow the equivalence translates as an isomorphism of those homologies. Well, usually we can define much more stuff than we can compute. So when our homology theory is actually computable, we are lucky because then it provides abstraction of two objects being equivalent, and we can define further, like more complicated or like other structures coming from the homology theory, for example, Poincare polynomials, Laurent polynomials, or in algebraic geometry, Hilbert polynomials, and polynomials like that somehow tells us something about the homological theory that appears in topology. However, in our setting, the homology is very hard to compute. And so we somehow have to, we are forced to simplify our situation. And for that, we will use today augmented chain complex, which is basically a chain complex with a chain map to our ground ring based at degree 0. And we also want the equivalence of spaces to be translated via our construction to some equivalence of those DGA maps. And this actually will yield a new homological invariant that is computable, and then we can do the story over again and we get some polynomials as above. So this is the philosophical outline of my today's talk. The more precise structure is that we will define what a contact manifold and Legendrian manifold is. Let me remark that we will limit ourselves to a particular setting. Then we will define Legendrian contact homology, which will be our homological theory, our augmentation, and our bilinearization, which will be our simplification. Then I will talk a bit about two sequences, long exact sequences or actions of two constructions on our homological theory that we will use to prove DGA-homotopy criteria. And if the time will permit, and we will see, I will comment a bit about the kinds of Laurent polynomials that appear as Poincare polynomials of our homological theory. So let me start with the setting. We will work with one-jet spaces, which arise from an m-dimensional manifold M, as a product of a cotangent bundle with line. Here the subscripts denote the coordinates on the cotangent bundle, P for the position and Q for the momentum, coordinates, and we can define one form, differential one form, which is written there, as you can see. It's alpha is equal to dz minus q dp, and the kernel of this one form gives rise, because it's one form and we have 2n plus 1 dimensional manifold, and so the kernel of this one form is a 2n dimensional hyperplane distribution, which we called Xi. It is called a contact structure, and one-jet space with this contact structure has a structure of a contact manifold. This is a particular case. We can define it in more generality, but if you're interested about this, you can ask me during question time, because the results that I will state work mostly in settings very similar to one-jet spaces. So in this case of one-jet space, we also have a special vector field R, which is d over dz, which is I will usually draw it as the vertical coordinate, as the vertical line. And to be understandable, we here have a classical example, which is an example of a standard contact manifold, which is just an odd dimensional manifold, which we coordinate using x1, y1 to x and yn, and z is again the vertical coordinate. And there the contact form has a form, as you can see, with a real vector field, which again coincides with the vector field d over dz. So at the bottom of the page, you can see the picture of a standard contact structure in R3. So those are somehow twisting planes, and you can imagine that it is Z invariant. And so it doesn't really matter at which level you find yourself at the point of a time.
Question.
Yes.
Did you make the picture by yourself, or?
No, I just downloaded it from Wikipedia.
Okay, thanks.
However, this next picture, I know the author, not personally, but I know the author. So our space that we will study will be Legendrian manifolds or submanifolds of one-jet space. So here we can fix a topological type lambda and n-dimensional manifold, and we define Legendrian embedding as an embedding so that the differential of the map sends the tangent space of my manifold to the hyperplane distribution. And okay, then the Legendrian submanifold is an image of an embedding like this. And again, an example, in R3, we consider Legendrian knots, which are embeddings of S1, which are Legendrian, and being Legendrian in this case corresponds to satisfying the partial differential equation that you can find on the right hand side. That's y is equal to dz over dx. So there you have an example of a Legendrian knot in R3. It's a Legendrian unknot, and this picture is by Joshua Sabloff. And I think you can find it on ResearchGate if you would be interested. And okay, so we see that there are those hyperplane distributions drawn, and they are drawn to projections. So one of the projection is so-called Lagrangian projection. That's the projection to the XY plane. In case of a one-jet space, it's the projection to the cotangent bundle, the canonical one. And the other projection is so-called front projection. And that's the projection of the knot to the plane, which is XZ plane. And in the case of one-jet space, it's the PZ plane. So basically projection to the product of the manifold times R. Okay, so what can we see here? So if I pig color, for example, blue. In here, we see, let me enlarge it. In here, we see that we have a double point in the Lagrangian projection to the XY plane, and it actually corresponds to an integrated REAP vector field, or to an integrated, or to a segment of integrated REAP vector field that is called the REAP chord. And in the front projection, it projects like that, where it is found at places where those two tangencies are parallel and horizontal, or parallel. Not they don't necessarily have to be horizontal. So we actually have an a bijection in between the REAP chords and the double points in the Lagrangian projection. So those are our spaces. And now what will be our chain complex, and of course the equivalence relation. So the equivalence relation is Legendrian isotopy. What it is just a smooth homotopy. At each point of a time, we have a Legendrian embedding. And we will, of course, study those Legendrians up to the Legendrian isotopy. So as you can, because of course we already have seen that the knots, Legendrian knots, are classical example and are free. Somehow the study of Legendrians up to this Legendrian isotopy retains a lot of features of low dimensional topology, even in higher dimensions, and a lot of features that look very similar to knot theory. Okay, but because the class of Legendrians is very broad, we will restrict ourselves to a subclass of Legendrians where we can define our theories properly. So we will restrict to Legendrian submanifolds which are closed. That assumption will be used to have a finite number of those segments, REAP chords. The second assumption is that our chords will be non-degenerate. That will allow us to do some J-holomorphic analysis, which I actually won't digress that much on. And the last assumption that we will make is that we will assume that the Maslov class will vanish. What Maslov class is, it's kind of a homotopical feature of our Legendrian, and it allows us to have a Z-graded theory. With non-vanishing Maslov class, let's say we would have a Maslov class with which would be equal to some R, which would be an integer, we would get a cyclically graded theory, which is okay, but in our case, we will consider the Z-graded one. So what is the topological theory then? So the theory, the construction which provides us with the chain complex was first defined by Chekanov, and then after Eliashberg and others devised the framework of a symplectic field theory, it was generalized by Ekholm, Etnayer, and Sullivan to Legendrian submanifolds in higher dimensions than just 4 knots, as it was done by Chekanov. So what the theory is, we will consider a Z-graded vector space over Z2, generated by our REAP chords and graded by a shift of Conley-Zender index, so that the CZ in there doesn't mean the Czech Republic, but the Conley-Zender index. And we will take its tensor algebra, TV. We will grade it so that the field lies in the place with a 0 grading, and then we extend the grading additively onwards. And because we want to define differential graded algebra, we define the Chekanov differential. and it is defined in the following way. So there we have some counts of some space, that's this part of the differential, and some words. So what does the discount actually mean? Well, there we count some solutions of second order nonlinear partial differential equation, which I will explain, which is explained on the bottom of the page. So let us go there. So this space MA and B1 to Bm is a space of so-called space holomorphic disks with the positive puncture at the Reeb chord A and negative punctures at the Reeb chords B1 to Bm. And how is this pseudo-holomorphic disk defined, what it actually is? So we take a disk in R2, a unit disk, and we remove from its boundary several points. The boundary of the disk is drawn there in red, and the points which are removed are denoted by a little blue cross. And the top puncture, we will say that the top puncture is positive and the two punctures are negative. And the pseudo-holomorphic disk is a map from this puncture disk to symplectization of my one-jet space such that they satisfy a form of Cauchy-Riemann equation. So what is the symplectization? I simply add a direction to my one-jet space, which is odd dimensional. So now I have an even dimensional manifold, and I have a contact form alpha, which is my contact form, and I define a new symplectic form on the symplectization that is given by this simple formula. So I have a symplectic manifold, and I can, if you know a bit about it, that means that I can find a compatible, almost complex structure. And so I have J on one side, which is the small j, that's a complex structure on the disk in the plane. And I have almost complex structure on the symplectization. And I will require that my map satisfies the following thing. So the tension map should be holomorphic in this sense. So that means that it commutes with respective almost complex structures. And okay, so that's what being pseudo-holomorphic means. Now, what gets mapped where? So this upper positive puncture at infinity, we will let it approach this chord A, which is, let me enlarge it a bit so that you can see it, to this chord A. And in minus infinity, we let the map to approach to those two chords B1 and B2, where the positive and negative, let's say, decoration means that the positive direction, the positive chord somehow respects the orientation of the boundary of my disk. So we are somehow flowing with the flow of the Reeb vector field there. And the negative puncture means that in here, we are flowing against the Reeb vector, against the Reeb vector field, or the flow of the Reeb vector field, which we have chosen. Okay, so this is a very complicated and messy picture. What it actually is that we somehow combinatorially count pictures like this, which are on the right-handed side here, and where A is a positive puncture, and here B1 and B2 are the negative ones. So if we are lucky enough, spaces of those solutions actually have a structure of a smooth manifold, And the dimension formula for the smooth manifold can be found here in the lower right corner, which is basically the grading of the upper chord minus gradings of the negative chords, and then the -1, and there is -1, and that corresponds to the fact that we actually here, when we just, if we wouldn't subtract the 1, it would mean that we would consider all the maps also with the reparametrization in the R direction, because you can write out the equation and see that it's somehow, when you reparameterize it in the shift it in the S direction, either way, you basically have the same map which produces an R family. And so we are modding out this, and that's why the -1 is appearing there. Okay, so which curves we count? We count curves which are somehow rigid. And the rigidity, it means that my moduli space is just a set of points. I cannot wiggle in the moduli space. So that means that my moduli space has to have a dimension 0. Okay. So to have a proper homological theory, to have a proper chain complex, one has to show that the differential squares to 0. And this was for higher dimensional case proven by Augmentations and Sullivan using trick which is standard in symplectic topology and is very reminiscent of Morse theory. So I can digress a bit on the trick in the slide there at the bottom. So imagine that you try to compute d squared. So you say that you compute d squared of a, and it's a word, it comprises of a word, and you have a word b2 there. Okay, so this b2, then, okay, sorry, it's not squared here, this is just the differential of a, and then you compute d squared a, so you send the differential on the first dots and then the differential on b2 and the differential on the rest. Okay, so what it actually is, if you compute the differential, you have two counts of some rigid pseudo-homomorphic disks. So let's assume that u1 corresponds to the count of the pseudo-homomorphic disks for the first differential, the differential of a, and then the u2 corresponds to the count of the rigid disks for b2. Okay, so now if I draw them like how I drew them, you see that I can somehow glue those two disks at the puncture which gets mapped to b2, and by gluing, I obtain a new pseudo-homomorphic disk. Well, if I'm lucky enough and I do the analysis very carefully and properly, I can somehow compactify my space of solutions, and I somehow can converge to a boundary point of my space of solutions. And there on the boundary sits the curve U bar, which has which looks like this, has 4 negative punctures in this particular case, and we would like to know what is the dimension of the moduli space that we work with, because only curves that we count are the rigid ones, and the rigid ones means that in the dimension formula we have to get 0. So if I write the rigid condition for the first disk, that's this equation 1 here, and the rigidity equation for the second disk regarding the grading for the chords, for the curve 2. And here I realized that I made typos everywhere, because of course this should be grading. So you can imagine that I have grading here everywhere. So we know that these two things hold, and so when I then want to compute what is the difference of the grading of the positive puncture and negative puncture here for the for the curve u bar, I write it down, and to count it, I need this formula to be equal to 1. But using the equation 2 here and equation 1, I get 2. And so it means that this curve u bar is a boundary point of a compact, that is important, compact one-dimensional manifold. And because compact one-dimensional manifolds are just circles and line segments, I know that the number of my boundary points will be even. And so I get 0 in the differential. And this is the philosophical reason, or this is the idea why the differential squares to 0. And that enables us to define so-called Lagrangian contact homology as the kernel of the image. And again, Eckelmann and Sullivan for higher dimensional Lagrangians proved that this homology theory is an invariant of Lagrangian isotopy. Well, that is nice that we have a theory that we have an invariant, but to actually use it in practice is very hard. It's very hard to compute. It's often infinite dimensional. And so we need to simplify our situation a bit. And that we will do using augmentations. So again, for us, an augmentation will be a DGA map. So we already have our Chekanov-Eliashberg algebra, which is our complex, which we defined before with the differential. And we will see our ground field as a chain complex concentrated at degree 0 with a 0 differential everywhere. Sorry. Well, then augmentation is just a DGA degree 0 homomorphism from the DGA to the ground field. When I see them as chain complexes, and we can define something like a prism operator in standard simplicial homology. Somehow a map that if I take 2 augmentations, it satisfies the formula which is written there. So KAB is equal to E1A KB plus KA epsilon 2. Oh, there is a typo. There should be.
Excuse me, Filip. You told that the homology is a module over the ring of some bigger ring, not just complex or real numbers. Yeah, is it somehow evident, or is it easy to see that it is a ring of, I guess, some kernel of some differential which you denoted by 0, called by D0?
You mean this theory, or I understand. Let me write it out. Okay, so this homology theory is, I take my chain complex of my Lagrangian lambda, which is defined by, which is given or generated by Reeb chords with the Chekanov differential. So this, it has degree -1, and it goes like this, -2 lambda. So, and those things are just vector spaces. Yeah. And the algebra structure there is just a tensor product. So what do? You have a chain complex, and you have a chain complex over Z2, and you have the differential. Yeah. And sorry, this is not really the thing that I said is not really true. This part is graded, and the grading is here, z or dot or bullet -2, grading of my TV, where we was the thing. So there the complex is difficult because I consider all words with grading, I don't know, n. And so at the place of a grading, I don't know, n, I can have some segment of the tensor algebra, which is already infinite dimensional. So that's why it is so hard. However, the coefficient ring is always, for us today, is over Z2, always. Not over Z, not over any more complicated ring.
Okay, so no Leibniz rules for tensor products or
you actually, to have it defined, this differential, you define it when you have two ripcords of some grading here, where the grading of A1 plus times A2 is the sum of two ripcords, and so the differential is just defined by the form of the word, is defined in a formal way. So we have differential of A1 times A2 plus, then when you don't work over Z2, there is some minus sign. So if you would be otherwise confused, we can write it, but it's not there because we work over Z2. So it's on the words, we can extend the definition of the differential via Leibniz rule.
So as a graded homology, it is a module of a ring you introduced. As a sum of these all gradings, yeah, because
we do it just in the formal way.
Yes. It doesn't go endomorphically. Thanks. Sorry for this.
No, it was absolutely great question. Okay, so let me then go back to those augmentations. So we have two maps of two chain complexes, and the augmentation is the chain map, which is more what it satisfies is the Leibniz rule. So it's a DGA, a map of degree 0, and we can find if we have two augmentations, we can find a prism operator, or as we call it here, an epsilon1, epsilon2 antiderivation, so that the equation here is satisfied. And if such an antiderivation actually exists, then we say that those two augmentations are DGA-homotopic if this equation here is satisfied. So the difference of values of this augmentation is an image of a cycle in the antiderivation. That's what it actually means. And we define a set curly E, which is, or big epsilon, and that's basically the set of all DGA-homotopy classes of augmentations. Yeah, it might be hard to imagine, and it is actually extremely hard problem to determine whether two augmentations are DGA-homotopic or not. And basically the rest of my talk will be somehow, the backstory will be the question whether two augmentations are DGA-homotopic or not, and how to detect that. So, okay, but to do that, we had some very formal algebraic construction, but we actually know that it arises in geometry. So how it arises in geometry. So we can imagine that we have an exact Lagrangian filling of our Legendrian in this symplectization. That's a lot of words, but what it actually is, it is a manifold L, of which our manifold lambda is a boundary. And you have a picture on the bottom of the slide. And this L is an exact Lagrangian manifold, which means that if I would pull back or restrict the symplectic form on this manifold, it would be exact there. Okay, so how the augmentation arises. So having such a filling, we can again define another count of another solutions of a perturbed PDE, of a nonlinear second order PDE. And the count is defined as follows. So we count again over some rigid objects. And those rigid objects will be punctured disks with only one positive puncture and with the boundary mapping on the Lagrangian filling. So the picture of the count is at the bottom of the slide with this puncture mapping to this chord here, which is chord A, which is a positive puncture. And this construction is very nice, because then if we have an isotopy through exact Lagrangian fillings, it defines the same count in a way. The same in a way means that the resulting augmentations are DGA-homotopic. Okay, so that was proven by Ekholm, Honda, and Kalman for knots. And I'm sorry, I forgot to, I should probably mention that Karoshan observed that it translates, the proof basically translates word by word for fillings and Legendrians for bigger dimension than just for knots. Okay, so we know what the geometric origin is, and we will keep that in mind, because augmentation is just choice of disks with positive puncture.
Let me just say, Filip, that what Cecilia Karlsson did was, so basically there is also extension to more general coefficients. So whatever she did works also with Z coefficients. So, you know, like when you have Z and some extra topological information. So yeah, it's not just extension to high dimensions, it's also extension to different coefficients.
Yeah, and she did it over Z or ZH1 of
well, it was the ZH1 of I think of a Legendrian.
Yeah, you're right. I'm sorry. Yes. Okay.
Or so maybe it was even ZH1 of the coordinates. Probably it was ZH1 of the filling or something.
Okay, great. Thanks a lot for the remark. That's great. Okay, so we have a geometric origin of those augmentations, and now we can somehow simplify our differential, which is very difficult and produces creates a homology theory which is almost impossible to compute. And we will simplify it in a way that we get actually complexes of vector spaces. And there, with a differential which will be quite tame and which will produce a homological theory that will be actually computable. Okay, so at the top of the slide, we see the original Chekanov differential, which is complicated. And then Chekanov in his paper devised this linearization procedure, which means that he somehow killed off first k-1 letters in the tensor he kept the kth one and he killed the rest also. So what is the idea behind this algebraic formula? The idea is that we have our count of our rigid pseudo-homomorphic disks, and we have a filling, and there the augmentation is count of the disks. So we with one positive puncture, so we somehow glue or decorate our negative punctures with those disks or with those augmentations. So the formula above would actually translate to a picture which you can see on the right hand side. That means like by augmenting that, like augmenting is just gluing or decorating using disks. So this theory is nice. However, we discarded a lot of information, and we discarded too much of the information. So with the differential defined above, we see that our differential doesn't increase the length of the word. Our differential goes like reads one ripcord and spits out a word which in each ripcord has just length 1. And that means that we can restrict ourselves to just the vector space generated by the ripcords over Z2 and with the differential as above. And we know that if we somehow decorate this differential using two augmentations which are DGA-homotopic, then our theories will be isomorphic. However, because we discarded...
Philip?
Yes?
Yeah, so you last formula, you say that the epsilon of lambda is a set of how to say, augmentation. You're right?
Yes,
but no, you define only for Lagrangian filling, and a Lagrangian filling is only subset of augmentation, or so how, right?
You're right. However, first I define the augmentation in this algebraic way. So not this. This is amazing a remark. Also, not all augmentations arise from this embedded exact Lagrangian fillings. We can have augmentations which doesn't really necessarily come from this. There are some conjectures telling us that they might arise from fillings, but not embedded ones, but immersed ones. So, and that's a hard conjecture, and no one, as far as I know, no one knows whether it is correct or not.
Okay, thanks.
Yeah, you're welcome. That was also an amazing question. Okay, so having this linearized Legendrian contact homology, we have something, but this homology theory that we produced is no longer a Legendrian isotopy invariant. So how to get out of it? We have to consider somehow a set parameterized by all DGA-homotopy classes of my augmentation for my Legendrian lambda, and I have to consider all the homologies for this Legendrian, and then the set is a Legendrian isotopy invariant. So by discarding this non-commutativity, we actually had to consider not a single homological theory, but set of those. Okay, but that is not enough. We discarded just too much information, and now we somehow want to retrieve some back, and we can do such a thing using two augmentations, epsilon1 and epsilon2. So it is basically the same slide. However, I use epsilon1 for the first k minus ripcords, then I let the k cord to survive, and then on the rest I use epsilon 2. That is an idea due to Bourgeois and Galant. And using this differential where we use two augmentations and the order matters of whether the epsilon 1 is first and epsilon 2 is second. So this notation is important. We define a Legendrian contact homology, which is bilinearized again, and which produces this. It is a vector space over Z2, finite dimensional. We again know that if we have homotopy, DGA-homotopy of two augmentations and another augmentation, then we have isomorphic LCH, bilinearized Legendrian contact homologies of the same Legendrian. Oh, and I see there is a misprint. There should be lambda and not L there. Well, correct that. So there should be lambda here because our Legendrian is lambda. Okay. But even though we retrieved some of the non-commutativity, that's still not enough to have a Legendrian isotopy invariant. And we again have to consider a set which is parameterized now by the product of the sets of DGA homotopy types of augmentations and all the homological theories. Of course, the set that we had before for linearized Legendrian contact homology is a subset of this new set. And so the bilinearized Legendrian contact homology somehow has more power, is more refined invariant, mainly because we somehow retrieve parts of the non-commutativity. Okay. So that are definitions, and now what do we know and what can we do with it? So the J-homomorphic invariants and counting some solutions of Cauchy-Riemann equations are quite rigid. Objects are somehow very vaguely reminiscent of algebraic geometry, but with complex structures which are not necessarily integrable. And so it is absolutely astounding that there is a connection to topology and of my Legendrian, and the topology somehow comes into the play when I want to do Poincare duality for this relative SFT. So for simplicial homology, we know that for closed manifolds, we have some pairing, which is non-degenerate intersection pairing, which provides us with the isomorphism of homology and cohomology. However, in here, if we define the cohomology theory in a formal way, so the differential is in the formal way defined as this, using pairing on the Reeb chords. We don't have the isomorphism. The pairing is not non-degenerate, and somehow the degeneracy of the pairing can be encapsulated in this long exact sequence connected linearized Legendrian contact homology, cohomology, then linearized Legendrian contact homology, and then the simplicial or Morse homology of my manifolds L, and then cohomology again. So there we have some pairing which is used to define this formal dual, and the pairing is deformed in a way that the following identity holds, where we have two maps on the right-handed side we have the intersection pairing from the Poincare duality of the Lagrangian submanifold, and on the left-handed side we have the formal grading, formal pairing on Reeb chords, and maps sigma k and tau k count the following configurations of J-holomorphic disks and negative gradient flow lines of a Morse function on my Lagrangian submanifold L. So suppose that I take a critical point of an index n minus k of a Morse function on my manifold and some Reeb chord of a grading k. Then T dot, or in this case, T k q counts disks, pseudo-holomorphic disks with augmented negative punctures and with a negative gradient flow line attached to a boundary flowing to the critical point C. And the map sigma somehow counts a dual configuration, let's say, and that's basically the same curve, but the direction of the flow is somehow flipped. Also, the direction of Q should be flipped. So that's a typo. Okay, so that's the way how to connect two theories. One Morse one is very wobbly and topological, and the J-holomorphic one is rigid. And we have actually almost all the ingredients to prove this DGA-homotopy criteria. And I'm not sure if I froze.
You didn't.
I froze. My computer froze right now. Do you see the slides?
We do see the slides. Maybe your computer froze, but the presentation didn't, I think.
Okay, that's great. So I remember the slides. So I have a black screen in front of me. So, okay. So you can, okay, let us recall that the DGA-homotopy of two augmentations were defined in a way, was defined in a way that we had the difference of two augmentations and some antiderivation and some differential. And when we had this antiderivation, we could define something like this. So but this antiderivation was somehow a map of algebras. And here when we do Legendre contact homology, we just have a Legendre linearized or bilinearized Legendre contact homology. We have just vector spaces. So we can actually prove that if there is an antiderivation, if and only if there is an antiderivation, there is also a map of vector spaces, so that the identity, which is very similar, holds. I think I denoted it by K bar there. And okay, so that is one way that works both for linearized and bilinearized differential. And in the connected case, because there are two cases for which we somehow can try to somehow characterize when two augmentations are homotopic or not, and that's for linearized, for connected case and for disconnected case. For connected case, it is done. Oh yes, it appeared. Okay, that's amazing because I want to draw pictures. For a connected case, it's done in a way that on a chain level you can express this map tau 0 from the duality long exact sequence as a difference of those two augmentations. So how it is done, we know that the map T0 somehow counts configurations like disks with negative gradient flow line attached to it, flowing to the critical point. But because we can arrange stuff in a way that our endpoint of our ripcord Q in this case lies in the stable manifold of my minimum, we somehow have an open, like, mapping to the stable point is somehow an open condition. So the boundary of the disk would somehow, if it wouldn't be rigid, if it wouldn't be a single point, we could attach several gradient flow lines to it, moving, okay, I hope, like this and like this. So if I would actually, okay, if the image of my curve wouldn't be a discrete point, I would get a count of the moduli space which is not rigid, because I have one-dimensional family in it, and the one-dimensional family would differ by sliding of this marked point and this negative gradient flow line, and so I cannot have a non-discrete image of the boundary, and so my disk here is kind of boring because it somehow maps, it's a strip where positive and negative puncture is this ripcord Q, and it matters where you put the marked point. If you put it on the left-hand side, you go from the bottom, and if you put it from the top, if you put it on the left-hand side, you go from the top, and you put it from on the right-hand side of your curve, you go from the bottom. So you have some two counts, and those two counts are precisely epsilon1 minus epsilon1 to y, because that's precisely what happens when you decorate the chords. Okay, in the disconnected case, one can actually one cannot say anything like that. Even on the chain level, this statement doesn't really make sense. However, using an effect of a surgery very carefully, one can surgery the disconnected Legendrian submanifold in a way so that one can reduce the problem of DGA-homotopy of the original augmentations to some problem of DGA-homotopy of another augmentations that actually live on a connected Legendrian submanifold, which is in this case should be denoted by lambda s, which is the searched one. Well, and because I have 2 minutes, I won't digress that much on the details of those proofs or on the effect of Legendrian ambient surgery for Legendrian submanifolds, but I will say the statements of the DGA-homotopy criteria. And that if you see here, if my map tau 0 has an image which is, if it vanishes, if the image is just 0, it means that indeed epsilon1 has a minus epsilon2 has to be an image of a cycle that happens in the connected case. So if it is 0, if and only if those two augmentations are DGA-homotopic and is 1, because it goes to age 0 of your Legendrian, and that's just the class of a point, so that's a line. So if it's 1, if the dimension of the image is 1, then you don't have DGA-homotopic augmentations. That was proven by Bourgeois and Galant. And then there is a generalization to disconnected Legendrian submanifolds, and which says that those two augmentations are homotopic if and only if the fundamental class of your Legendrian lies in the image of the map tau n from the duality along exact sequence, which somehow describe the deformation of the Poincare duality for this SFT, where this fundamental class is the top homology class of your Legendrian, which actually splits to the sum of components of to the sum of top homologies of the components. Okay, and that's I'm out of time, so no encore. But okay, can I? Yeah. So this is what you missed, and thank you for your attention. And yeah, that's all.
Thanks a lot, Filip, for the talk. Are there any questions, comments?
So that is Filip, your paper. That is a note on geography here and noted on archive.
It is on archive yet.
Because you didn't put your archive identifier here. So
oh, what are my archive identifiers? Oh,
yeah. So could you please add it and then send the corrected version? Yeah. To Roland.
Okay. Okay, I will.
So that you proved last year?
Yes.
That's very nice. I enjoy your talk. Yeah, very good talk. Yeah.
Yeah, thanks a lot.
Filip, a very basic question from me. So probably you've been asked this question many times, but do you expect some, like extension of your result when you consider more general coefficients?
Yes, I'm thinking just about this right now. And okay, so the problem is follows. So when you can do this Chekanov-Eliashberg algebra over more complicated coefficients, and you can do it over loop space coefficients. And it seems that if you just do it over Z2, you discard a lot of information. Then if you pass to Z2, you gain something. And if you work, for example, then you can go over like group rings of your Legendrian, and that already detects much more things. This is nice if your Legendrian is a tori, because if you have base loop space of a tori, what it actually is, well, the loop space of a tori is contractible. It has the zeroth the homotopy group of this thing is Z times Z, and higher homotopy groups vanish for n is bigger or equal than 1. And so when you do homology, you should, because it's contractible, you get like only if you would do it over some like this basically corresponds to doing it over this thing. Of course, when you do it over chains on loop spaces, then it's very hard. I don't know it, but I'm thinking about it. But to do this, one would have to somehow generalize the duality statements and reprove things for loop space coefficients. But I think that's doable. And I think that what it actually would then entail, and the thing which would be interesting, is that we have this geography question. And the geography question somehow tells you that you have some theory, some homological theory, and it produces using this construction of Poincare polynomials, some polynomials. And you can actually say which polynomials are admissible. You can somehow identify the image of this map. But for two Legendrians, if you have Legendrian and over one Legendrian, we have somehow like fiber, or like I imagine the Legendrian, and then the fiber is somehow parametrized by the augmentations. And in other Legendrian and its fiber, those are, and they might be Legendrian non-isotopic, in like totally two random Legendrians of the same topological type. they can be sent it using this map to polynomials which somehow are the same. Like this polynomial in here, this intersection in here would be the same polynomial. And that's actually an inverse question, which is called botany question. And I now try to what I'm doing now, I'm computing some DGAs over loop space coefficients and the chains of loop space of the DGA coefficients. And I think that it has some connections for torics to unknotting, to somehow higher dimensional unknotting. And then this, like if I do the bifurcation analysis for the spaces of those solutions of those perturb or nonlinear PDAs correctly, I would be able to describe the defect of one Legendrian passing through each other, like one handle of the Legendrian passing through each other, which is something what is happening when you do unknotting of two knots. You somehow cheat. You admit it to pass through each through itself. So if I would be able to describe the action of this thing happening, then I would be able to produce maybe two non-isotopic Legendrian submanifolds with the same Poincare polynomials, and maybe this intersection of fibers would then, using the unknotting procedure, would somehow tell you what kind of embeddings meet here.
But there are some examples like that, right? So basically, for example, there was a what's the name? There was a paper recently used in particular by I believe Baptiste and Noemi, where they talk about the standard unknot and this knots that have a basically stable tame isomorphic Chekanov-Eliashberg DGA, the whole infinite family, but they are all not Legendrian isotopic to the original Legendrian. So the algebras are actually stable tame isomorphic. So in particular, all the information, like whatever you do, like all the Poincare polynomials will be the same because the algebras are actually the same. They're the same from the algebraic point of view. But the knots themselves are not Legendrian isotopic, right? So there are examples like that. These examples are known, and they are known even in low dimensions. In high dimensions, it's an interesting question actually what happens to them. Will they become, for example, Legendrian isotopic after you do some stabilization or whatever those Legendrians? But examples like this do exist. So just as a side remark. Maybe you already know about them. Maybe I just interrupted yourself or whatever.
No, I didn't know about this example, but yeah, that was just a cute application or a nice application of what I am computing right now, because I do this perturbation analysis for some other reasons, but it would actually in higher dimensions tell you something maybe more interesting, and then maybe in not contact homology, but that's a different story.
Right. But the examples I mentioned, this are once again the standard unknot and so-called Legendrian realization of pretzel knots P3 minus 3 minus n. So I believe they took them from, if I'm not mistaken, from reasonably old paper of 1 second. Let me find. Yeah, of paper of Cornwall and Civic from 2016. So yeah, just as a side remark once again. But yeah.
Yeah, thanks a lot.
Are there any other questions, comments, maybe even concerns? Who knows? If not, then thanks a lot, Filip, from me, and I believe from all participants. And I believe we can close the session.
Okay, thanks a lot too for your attention, and it was great to hear you again.
Great. See you soon in Prague.
Yes, see you. Bye.
See you.